a continuum approximation approach that is able to optimize two distinct network layouts, as you will see from the screen. One is the ring-radial, and the other is the grid string networks. And they will be optimized for continuously varying spatial geometries. So we're going to start from some background information. I will first note that there are thousands of cities with distinct topologies. Here we just show some examples, and you will see that the street networks of these cities are largely different. The first one is Beijing, second one is Hong Kong, third one is Miami. And however, most of the cities will exhibit one of the two basic structures, will be similar to one of the two basic structures. The first one is the ring-radial. Here I showed Chengdu of China for an example. And the second one is a grid network. Here I show New York City for the example. And those two network structures are the focus of this presentation. We also know that the transit network design is a complicated problem because of the various city forms, physical and geographical details in street networks, demand, transit technology, service constraints, etc., etc. And the question regarding transit network design is, shall we incorporate all the details once and for all, or start from certain idealization and then generalize it to the real city network? So this question has led to two different classes of literature in this realm. Here I'm not going to convince you that one is better than the other, but just to show that each class has its benefits and flaws. So the first class is the so-called discrete models that incorporate high levels of real-world details into the models, including the geographical constraints on route and the stop locations and specific OD demand, origin destination demand. To their credit, designs derived from those models can be readily implemented in the practice. However, those models usually require heuristic methods with high computational costs, even for a single transit route. And also, due to this high computational burdens, the solution space was often limited to a select number of route and stop location candidates, resulting in suboptimal designs. Moreover, those discrete models unveil little general insights into the causal relation between input parameters and optimal design variables. Thus, the models are usually not universally applicable to a number of cities with distinct street networks and demand patterns. So here we introduce the second class of models, the so-called continuum approximation models, which use smooth, continuous functions of densities for line, stop, and demand to approximate the numerous discrete parameters. And these models are developed from usually a presumed general network form that presents the city shape and the street layout. For example, a ring-radial network or a grid network, but are not limited to a finite set of routes and stop candidates. These continuum models are much more computationally efficient than their discrete counterparts, and global optimum and even sometimes closed-form analytical solutions can be obtained. And more importantly, the idealization rules, eliminates the second-order details and allows the key general insights to be unveiled regarding how key operating factors affect the optimal designs. However, unfortunately, the idealized designs are often not readily implementable. So again, here I compare these two classes of literatures, but I do not intend to convince you that one methodology is superior to the other. But we will focus on the continuum approximation approach and see how much we can achieve from it. So next, I will use a few minutes to show you some inspirational findings from the continuum models used in the literature. The first example is the optimal design of a transit route with many-to-many and heterogeneous demand. And I want to use this example to show you how continuum approximation works, and a key feature that proves to be very useful in our study too. So we look at the transit route at the bottom of this page. So since the optimal stop spacing will not be a constant because the demand is not homogeneous, the optimal stop spacing is not constant, then we just approximate it by a continuous function of a distance x. And we call this function s of x. And x just indicates a location. Okay. And note first that for a passenger originated at x, the average access time to the nearest stop is just the sx over 4 times vw. Here vw is the walking speed. So we can imagine that the passenger is going to access the nearest stop, and so the average distance the passenger could live just at the stop, or live just in the middle point between the two stops. So the average access time is just the spacing, the local stop spacing sx divided by 4 times the walking speed. That's very simple, right? And then note further that when a bus dwells at some stops near x, then all the onboard passengers will waste some time at the stop. And this time spent by one passenger within a unit distance around x is just tau divided by sx, where tau is the bus dwell time per stop. Note that tau is the time wasted by a bus per stop, and 1 over sx is actually the density of stops, or the number of stops in the unit distance. So this is the time wasted by one onboard passenger in a unit distance. Okay. So now we consider that only these two user cost components are related to the stop spacing sx. An objective function can be written as an integral. So this is the objective function to minimize the total user cost, but here we ignore all those irrelevant components. So we only have the integral for the entire length of the transit route, the access cost, which is sx over 4 vw times the boarding alighting demand, plus the time wasted at the stops, which is tau divided by sx times the number of passengers on board. Okay. So here I just I largely simplified the original formulation in the paper just to give you some qualitative descriptions. Then we will find that the integrands are location-specific functions. They are functions of x, the location x, and they can be simply decomposed to location-specific optimizations. That means the original optimization, the minimization of the integral, is equivalent to minimizing sx over 4 vw times the boarding and lighting demand plus tau over sx times the number of passengers on board for each x, which turns out to be an easy problem to solve. Okay, so this is actually the methodology where Xing and Gonem used to solve this many-to-many transit route optimization with many-to-many demand. And this location-specific decomposition is very useful, and this can simplify the original problem and decompose it to a location-specific optimizations, and it will be explored in our study too. A second example in the literature is De Gonzo's paper published in 2010 about the hybrid structure. So before this paper, we have already known that to idealize the structures of a grid network have been used. have been analyzed in the literature. First one is a radial network. So you see here that every transit line is a radial line. All these lines converge at the city center. And the second one is a grid transit line. So you can see that there are horizontal lines and vertical lines uniformly distributed over the entire city. And you can easily see that for the first radial network, you will invest less to the transit infrastructure because there are few the total infrastructure length is less. However, some trips might involve a lot of details because every trip, most of the trips will transfer at the city center and take another line. But for the grid network, you can basically eliminate these detours because for every trip you can basically take a horizontal line and transfer at any point to a vertical line. So basically you always choose the shortest path. However, there are many more lines and the agency cost is going to be higher. So the Gonzo's main contribution is that these two structures can be combined to a hybrid structure, which provides the so-called double coverage in the central area with perpendicular lines, with orthogonal lines, and a single coverage, which basically means the radial lines in the periphery area. So here, he introduced a new decision variable, which is alpha. Alpha actually indicates the ratio of the side of the square, the central area to the city side length. So this alpha is a new decision variable. And of course, when alpha is equal to 0, this hybrid structure just degenerated to the radial structure. If alpha is equal to 1, this hybrid structure becomes the grid network. So basically, we can see that this hybrid structure combines the both, and of course, it will achieve a better optimum, a lower cost than the radial and the grid structure. And this design actually is consistent with the distribution of passenger flows in the network. So here I used a figure from a different paper, but basically that figure deals with a similar problem. So basically there is a grid network, and we assume that the demand is uniformly distributed over the square. And then we assume that every OD pair, every traveler just chooses the shortest path over the grid street network. And here, the shadings basically shows the distribution of the passenger flows over the grid. The darker shading actually means a higher passenger flow. The lighter shading in the peripheral means a lower passenger flow. So it is clear that even uniformly distributed demand will result in the central area filled up with higher passenger flows. That means the shortest path trips will naturally concentrate at the center. And if we look at this hybrid network structure of transit, you will find that providing double coverage, which means a higher service frequency in the central area, is naturally consistent with the distribution of passenger flows over the network. That's why this hybrid structure is superior to the traditional structures. And here we will explore this hybrid structure in the ring-radial network too. Okay, so now we look at the formulation. So we're going to focus on two transit system configurations to identify the circumstances favoring the ring-radial transit systems versus the square grid systems. And for each circumstance, the optimal geometric layout and cost. And here, the circumstances in questions include the character of the city, which means the city size, the city's wealth level and demand level, demand density, and also types of transit technologies we use. So we will explore, for simplicity, we will explore circular cities for the ring-radial systems or square cities for the grid systems on the right. And we assume for now that the transit lines can be laid out anywhere within the circle and the square city. So this slide depicts two optimal configurations for two specific cities. Note how in the figure, both transit systems have a purple central area with two sets of orthogonal transit lines. In the ring-radial, there's in the central urban area, there are ring lines and orthogonal radial lines. For the grid network, in the central urban area, there are orthogonal horizontal and vertical transit lines. And also a periphery crown with only one set of non-crossing lines. In both cases, in the periphery, there are only radial lines. So our objective functions will include the user will be the to minimize the generalized cost, including the user cost and the agency cost. The user cost will include the cost spent by accessing or egressing the transit system, the waiting cost of a passenger at the original stop, and the transfer stops, the transfer penalties, and the time cost spent in vehicle travel. The agency cost will be related to the infrastructure length, the fleet size, and the vehicle kilometers traveled. The generalized cost objective function will be expressed in hours because we consider hours is a universally acceptable metric. So we can compare different cities with different wealth levels. So the decision variables will include the following. The first one is the size of the central area, which is just a number, a scalar. The radial line spacing is a location-specific function, which is actually a function of the distance from the location to the city center. So x, we call that x. So it's going to be a location-specific function. The line spacing will vary when x changes from 0 to the boundary of the city. The radial line headway is also a location-specific function. The ring line spacing and the ring line headway will also be location-specific functions. Of course, the ring lines for this ring radial network, the ring lines only exist in the central area. There's no ring line in the periphery. The headway of the outermost ring line is actually considered an independent decision variable, but that's just a single number. It's a scalar. And we will see why we will consider that headway independently. The stop spacing is considered a scalar. We consider stop spacing is uniform over the entire network. Okay. And so the decision variables will include totally 4 curves, 2 headways for ring and radial lines, 2 line spacings for ring and radial lines, and we denote these 4 curves, 4 continuous functions by dx. Here the d is bolded because we consider it as a vector. It includes 4 different functions. Okay, and the 3 scalars: the radius of central district, the circulator headway, and the stop spacing, denoted by a vector, the bolded symbol G. Okay. So here it shows a possible result of this design step. So we can simply see that the ring lines are not uniformly distributed, and the radial lines will bifurcate when the distance increases, the distance from the city center increases, the ring line, the radial lines will bifurcate to adapt to continuous function of the radial line spacing. Okay. So here we show the solution method. I will not bother you with the original formulation, which is very lengthy and complicated, which you will take maybe an entire day to check the details. So I will just show you some simplified, idealized representations of the mathematical formulation. So here, the decision variables are highlighted in red. For example, the first one is our objective function. F is the location-specific cost function, generalized cost function. And we integrate over x. Note that x is the distance from the city center to a specific location. When we integrate over x, we actually get the total. We actually get the total generalized cost. And here, G, here the h of dx and g is the location-specific constraint. So we have a set of location-specific constraints. So now the solution methodology actually is based on a feature that this entire mathematical program can be decomposed by the location. And first, we just assume this is true, okay. And then, if that is true, then we can condition on the global variables g. So we assume the g is fixed. For fixed g, what we can do is that we can minimize the objective function only for the location-specific function dx. And this entire program can be decomposed by the location x. That means equivalently, we only need to we can take off the integral sign, and we only need to minimize the location-specific objective function f for every x, for every location x. And this one turns out to be a much simpler subproblem, because this one is just an optimization of a continuous objective function subject to some constraints for only 4 decision variables. So now the 4 curves become 4 decision variables, and this can be solved by by applying some search methods. And then the result is going to be the d star of x for a given g. So that's going to be a function of the values of g. And then we just plug this optimal solution of location-specific functions for every x back into the original problem, and then solve for the global optimal. And this one turns out to be a function, an optimization problem with only 3 variables, and that will be also easy to solve. So basically, we're going to turn this entire problem into a bi-level program. The upper level is to solve this entire, to minimize this entire integral, and the lower level is for any given g, we're going to solve we're going to optimize the location-specific objective functions. So this method will work if the program can be decomposed by location. But it will be difficult to explain how this program can be decomposed by location without looking at the detailed, very lengthy formulation. But here I just show you some qualitative discussions. Okay, so for example, if we look at the local excess egress cost, the excess egress cost associated with the location x is actually a function of the local line density and local stop density. So that's going to be a function of only x. not other locations. The weight cost at each origin and transfer stop is going to be a function of the location-specific headway function. Location-specific headway. The in-vehicle cost, the in-vehicle time spent by each passenger at a specific location X is going to be a function of the local stop density at X, and also the passenger flow that passes through X. And we're going to stop here. We will not discuss more cost components, and trust me, the agency cost components can be similarly explained. So they can all be expressed as functions of X only. So all these functions will be functions of location-specific decision variables and local demand and or local passenger flows. So the question is whether local passenger flows can be a function of X only. And here we say local passenger flows can be determined if the routing rule is fixed. So this is an assumption we're going to make. And we assume the routing rules are fixed, and we assume the routing is determined by the shortest trip distance. So still take the ring-radial network as an example. What we see here is three different types of OD pairs. If we look at the first one, O1D1, which is inside the central area, the small circle encloses the central area. The larger circle is the city boundary. Okay. So for O1, so for a trip from O1 to D1 with a large angle, we will find that the shortest distance is through the city center. And this is also true for a trip originated in a periphery and ended in the periphery, and a trip originated in periphery and ended in the central area, or trip originated in central area and ended in periphery. All these trips with large angles will pass through the city center. But if the angle theta becomes smaller, for example, if we look at this the second OD pair, O2 from O2 to D2 with a small angle, then the shortest path is actually first to take the radial line from O2 to the ring of the destination, and then transfer to the ring line and travel to the D2. So this is going to be shorter than taking the radial line to the city center and transfer to another radial line to D2. You can see clearly that this arc is actually shorter than the two radius here. And if both origin and destination are in the periphery, still with a small angle, then because there's no ring line pass through D and O, so the only option is actually to travel through the radial line to the outermost ring and transfer to this outermost ring, travel to another radial line and transfer to that radial line into the destination. So this is going to be the routing rule for the ring-radial network. And given this routing rule, we can actually, before we find out the optimal design of the transit network, we can determine the passenger flows at every location. And this passenger flow turned out to be just a function of X. So eventually, this problem can be decomposed by location. So, so this is going to be solved with the methodology we introduced, and here we show some results. Okay, so we have explored totally 81 cases with two versions each. The two versions are for ring-radial network and for the grid network. And so there are totally 162 problems. And the 81 cases of each network type includes three different service areas means a small city, medium city, and a large city, and the three different demand density. We assume the demand is uniform here. So low demand density, medium demand density, and high demand density are three different values of time, indicating the wealth level of the city, poor, medium, and rich. And also include the three different technologies. There are numerous technology-related parameters, but we here just group them into three representative modes: the metro or the subway, and the bus rapid transit, and the regular bus. So the metro is the fastest and involves the highest agency cost. Bus is the slowest, but it's the cheapest, and the BRT is in between. Okay. So here's what we find. So we first optimize all these 81 cases for the two network types, and we compare the optimal costs between these two network types for each case. Here we assume that the city size will be the same for each case. Okay. So this figure shows the comparison. The horizontal axis just shows the optimal generalized cost for ring-radial network, and the vertical axis shows the optimal generalized cost for grid network. Note that this line has a slope of 1. So any point on this line means that the optimal ring-radial generalized cost is equal to the optimal grid generalized cost. Then you will find that all these points of all these 81 cases are above this line. So that means for every case, the optimal grid generalized cost is always higher than the optimal ring-radial generalized cost. And the difference was about 9% on average. So the grid is usually 9% more expensive than the ring-radial network. Why? We can explain this using three reasons. The first pertains to the degree of freedom of our models. We can say that the ring-radial configurations are more adaptable than the grid ones. For example, if you look at the central area only, the purple areas of the two networks only, we'll find that we allow the ring spacing and the radial, the ring spacing and the radial spacing to vary inside this central area. However, in a grid network, the spacings between lines are fixed. So that means we have more degrees of freedom, also more decision variables for the ring-radial network, and intuitively we will be able to obtain better results for the ring-radial network. So the second one is about the distribution of traffic flows of the passenger flows. To find out the distribution of the passenger flows, we now consider that if we take off this optimal, we don't consider optimal designs of the transit network. We just assume that there are lines everywhere. There are ring-radial lines everywhere, and there are grid lines everywhere. So the passengers will always choose the shortest path to travel. Then we try to find out the passenger flow that passes through a ring line at an arbitrary location. And for the grid network, we also find out the passenger flow that travels through a squared ring. Actually, this squared ring will consist of 4 different lines, but we just consider the passenger flows travel through the squared ring at every location, and we'll plot this passenger flows. And here's the result. So the horizontal axis is the dimensionless radius of x over r. This actually indicates the distance from the city center, distance of the location from the city center. And the vertical axis is a fraction of the total PKT. The PKT is the passenger kilometers traveled. So this is the fraction of the passenger flows of every line of the fraction of the passenger kilometers traveled along a ring line located at the station at the location X out of the total passenger kilometers traveled. So we're going to find out that the ring-radial network exhibits strikingly different pattern from the grid network. Okay, the first is that we find that the grid network always has a higher fraction of the ring flows than the ring-radial network. So that means if the structure is ring-radial, then the passenger flow on the rings will be much smaller. So it does not require a larger central area, because only within the central area there are ring lines, and we will see soon that the optimal results verified that. That means the central area of a ring-radial network is much smaller than of a grid network. And the second difference is that for a grid network, this fraction increases continuously until the end of the city. And for ring-radial network, it increases to some distance and then decreases sharply. So that means the ring flows, the passenger flows over the rings are more concentrated near the center for the ring-radial network. And for a grid network, the passenger flows are more dispersed. So we're going to say the concentration is definitely a good thing, because the transit system has an economy of scale, so it prefers concentrated demand. So when the demand of ring-radial network is more concentrated near the city center, then we can design more frequent services in the central area, and to better suit this demand and save the total generalized cost. And for grid network, the demand distribution is more dispersed, and that means it requires a larger central area and more transit lines to accommodate this demand, and it will result in a higher generalized cost. And the third reason is the average distance traveled is shorter in the ring-radial network. The first, this is because circle is naturally more compact than a square. But more importantly, this is due to the routing efficiency. So here, we just say if they can arbitrarily choose the shortest path, shortest trip distance, then we just plot the average trip distance as a function of alpha. Notice the alpha indicates the size of the central area, which is the ratio between small r and the big R for the ring-radial network, or the small d and the big D for the grid network. So when we plot the average trip distance, we're going to find that the average trip distance of grid is much higher than the average trip distance of ring-radial. When r is equal to 0, the difference is actually 25%. Even when alpha is equal to 1, the difference is 16%. So this means for grid network, passengers on average will travel a much longer distance. So this is one reason that ring-radial will beat grid for transit only. So we're going to summarize these three reasons. The outperformance of the ring-radial transit system is due to three key reasons. Okay, more degrees of freedom, concentration of trips, and also more efficient routing. Okay, now we look at the details of the optimal decision variables. First, for the ring-radial systems, how these line spacings and the headways will change over the location. Here, the horizontal axis shows the location of x from 0 to the city boundary, and this purple area indicates the central area. So we're going to find that in the central area, the ring line is which is illustrated by this network shown on the right pane. So you see the ring line spacing is decreasing, and the ring line we cannot see the ring line headway. However, the outermost ring is different. Remember that we designed the outermost ring headway as an independent variable, and the outermost ring headway is here, which is actually much lower than the nearest ring line. This is because most of the trips originated and destined in the periphery will use the outermost ring. The outermost ring actually carries a much higher demand than other ring lines. So we need to make this outermost ring more frequent with a lower headway. And if we look at the radial lines in the central area, we find the radial line spacing is actually increasing, and the radial line headway is increasing too, also as manifested by the right pane. And we note that they continue to increase in the periphery area. However, at the boundary of the central area, there's a discrete jump. So the radial line headway suddenly increases, the radial line spacing suddenly decreases. That means at the boundary of the central area, these radial lines bifurcate immediately. This bifurcation is to compensate the absence of the ring lines. But suddenly there's no any ring lines anymore, so the radial lines bifurcate to compensate that. So two important findings will be variable spacings and headways and discontinuity at the boundary. And then we look at the optimal designs of the grid system. So here we improved the Gonzo's model in 2010 by allowing the line spacings of the radial lines in the periphery to vary by location. However, in the central area, we see that all the radial line spacing and the ring line all the line spacings are constant, and also all the line headways are constant in the central area. So compared against the ring-radial system optimal design, there are three main differences. The first one is that we see that the optimal design of a grid network has a much larger central area. So the boundary is actually at here. For ring-radial line, the boundary is here. This is explained before because we just showed that the travel in a grid system is much less concentrated around the center. The second one is the spacing and headway for grid must be constant in the central area, and they are only allowed to vary in the periphery. And the third one is, as in the ring-radial system, the spacings between the lines and their headways decrease abruptly. So you see that the headway decreases and the radial line spacing increases abruptly at the central at the boundary of the central area. This is again to compensate the absence of a double coverage. But there is no need for a circulated line, so that's why we do not design a circulated line for grid network, because the periphery area is relatively small, actually much smaller. So there will not be much more demand to use a circulator. So larger central area, constant spacing, headways in central area, no circulated line. Now we just explore two more questions before we finish this presentation. First one is whether our method is better than simpler ones. So we define simpler ones as those with uniform spatial coverage. That means the line spacings and headways will be assumed to be constant. And these simpler models will be easier to solve because there will be no continuous functions to optimize. There will be only decision variables, a number of decision variables. And we tested the 81 cases, and the improvements are averaged slightly over 3% for both ring-radial and grid networks. So that basically means that the improvement is noticeable but limited. This also suggests that the spatial distribution of transit resources is a second-order effect. And the last question is about implementation, because we showed that the implementation over the real-world network is a problem for this continuous approximation approach. So what we do is that we do not intend to really implement that over a real-world network, but for each of the 81 cases, we try to adapt the optimal design of a ring-radial network on top of a grid network, and adapt the optimal design of grid network on top of a ring-radial network. So that means if we just totally mistaken the network type, we just apply the wrong network, what happens? We compare the cost of the adapted network with the original design, and here we show the results. The horizontal axis is the optimal cost of the original design. The vertical axis is the optimal cost of the wrong network, wrong design. And we see that, of course, all these points are above this line with the slope 1. However, these are just slightly above. These are very close to this line. So this shows that the misfitted network design is only slightly more expensive, averagely only 2.7% higher than the optimal cost of the correct design. So that means our model is very robust. So if in a real network, the structure is between ring-radial, it's like a combination, a mixture of a ring-radial and a grid, then we will expect that the cost difference will be even smaller. And of course, there are some other effects that we ignored. For example, the streets are not straight, and sometimes the transit lines, they have to do some detours. And these, we believe, will also not incur a much higher error. So if you are interested, you can refer to Estrada's paper, Estrada ETL paper in 2011, where they implemented an idealized network design to a real network, to the real street network of Barcelona. And they simulated various scenarios and found that the maximum error is within 5%. So with this, I just quickly presented some concluding remarks. We formulated analytical models for optimizing the transit network designs for ring-radial and grid networks with continuously varying spacings and headways. And we used the continuum approximation approach, which proves to be very powerful as long as the routing is fixed. And basically the original optimization can be decomposed by location and solved using simple search methods. And the findings show that the ring-radial is better than grid due to the striking difference between the striking difference in the passenger flow distribution and also the routing between the two network types. And the models are robust, and extensions for real-world implementation are possible. So here's what I'm going to present today, and thank you very much, and I will take questions.
Thank you, Dr. Gu. Very interesting work and elegant analytics. So, so the audience, if you have any questions, either you can directly ask from your microphone, or you can type your questions in the chat box. So remember that when you send out the question from the chat box, please select the send chat to organizers and panelists only, and then everybody will see it.
Any questions?
Okay, so while everybody is still composing their questions. Maybe I can start with one, so others can may throw out better ones. It's a very, I think, parsimonious analysis about very complicated systems, and I appreciate the methodology to use a continuum approximation or use this kind of homogeneous approximation to study a complicated problem. That reveals a lot of insights. So I wonder, I have two small questions. So the first one would be, so in your ring-radial network topology, so do you allow the spacing between rings increases with a distance from the center, or like here, so you have the distance between every two neighboring rings, right? Do you allow that distance increase with your offset from the center?
Yeah, we just optimize the distance as location specific function. We do not specify it will decrease or increase, but eventually optimal design shows that they will decrease.
Okay, interesting. All right. Okay. Oh yes, I see. So, so the solution is so the cost you presented there, was that the result directly from the continuum approximation, or you actually discretize it?
It's directly from the continuous approximation. So of course, eventually it's going to be solved by discretization, because we need to solve this location-specific optimization for every x, and there are infinite number of x. So we basically we're going to solve for as many x as possible, and then we connect these lines. So we get like an optimal location-specific function for the line spacings and for the headways. And then this one is actually an illustration. So basically, we just implemented the optimal designs by showing, because we cannot, because we have to like specify that for example, the radial lines will only bifurcate for finite times. So here we again use some discretization here, okay. But eventually the design is very close to the optimal design.
All right. So the cost you used in these comparisons are from the continuum directly
we use for comparison is directly from the continuous model.
Continuous model.
Yeah.
Yes. Yes. I think there will be a very few percentage difference between the continuous solution and the discretized solution. So
I think this difference is going to be very marginal, because basically when you discretize, the errors will cancel out.
Right. Right. So it'll be in. Yeah, I don't know, but I know it's marginal, but I feel like it might be interesting to know what is that error compared to the difference in the comparison. You know, if I believe probably the continuum approximation error, the error between discrete and continuous solution, if that is an order of magnitude lower than the differences that you show in the comparison, maybe that the result.
Well, it also depends on how you discretize it. So this figure I show here is just an illustration, and you can bifurcate. For example, you can bifurcate one radial line whenever you find that the total number of radial lines increase by 1, or you can bifurcate a few radial lines simultaneously. So these are the different accuracy levels you can reach by discretization. So here we do not intend to compare that. Actually, a more general question is, when this idealized design is applied to a real network, then how much is the cost increase? And we just, due to limited time, we just did not do that. And we are kind of confident about the results because Estrada did something similar, and they used a simulation. Actually, they involved the real street network, where like sometimes the lines will even like go backward, and they eventually find out that the difference is within 5% for all the scenarios they simulated.
Yes.
So we're kind of confident about that.
Yeah, I believe you. Yeah, usually the solutions are robust to local perturbations for location, for this kind of network design problems. So it's a very interesting thing that you know, there you have a circular ring line. The very outer layer of this circular ring seems like everything is continuous, but this one brings a huge discrete property to the formulation, because you know, there is a lot of jumps right at this boundary. So, so I just wonder, because when I thought about this problem, I would make everything continuous. But how did you get the idea of making that discrete, that boundary ring?
Oh, you mean for outermost ring only?
Yeah, for the boundary ring. So because when you do the continuum approximation, I would think that one model would just assign it, you know, assume that everywhere is continuous, and then there is
that's
no
just
clear
because
there is no clear boundary ring, but it looks like in your optimal solution there does exist that boundary that has a very outstanding discrete properties.
So basically, this one is originated from the answer of the 2010 paper of a hybrid structure. So we know before that the optimal design should have a double coverage near the center and a single coverage in the periphery. And then we make this outermost ring different from other rings because if you look at this routing picture, you will find that most of those trips originated and destined in the periphery will have to use this outermost ring. So the passenger flow along the outermost ring will be much higher than the inner rings. So this outermost ring has to be designed separately.
Yes. Interesting. So I know maybe in this study, because it's transit, maybe congestion is irrelevant in some cases, but you know, in some cities actually, there does exist some traffic congestion even at the you know, transit birch. You know, there's some queuing and stuff. You've looked at that as well. So if you're and also the interactions between transit and the street cars. Passenger cars. So if we can consider some of those congestions, would the localized, I mean, the very nice property of this problem that is localization analysis property, would that property be lost if you consider the congestion?
Considering congestion is going to be much more difficult. I currently don't have a clear idea about how to incorporate congestion in the network because the congestion is going to involve more complicated routing and also some kind of equilibrium things. So it will not be easy to tackle. But what you proposed is actually a very interesting question that pertains to a larger difference between transit and private vehicles. Here we just assume, so idealize ideally we just assume there's no congestion in the transit network. This of course can also be implemented in the real world because now like the transit vehicles, even buses, can enjoy some like a dedicated bus lanes and the transit signal priorities, something like that. However, if we talk about the congestion is more likely to be applied to cars. So here our major conclusion is that the ring-radial network is better than grid network for transit only, and this conclusion will not be true for the car network because for the car network, ring-radial network will constrain a lot of car flows near the center, and they will be very congested. The congestion will likely happen early and propagate faster than in a grid network. So this is, we believe, is a large difference between transit and the cars. And if we do consider congestion in the transit network design, I suppose it will also penalize this ring-radial design. So we'll make that less favorable.
Great.
I don't know if that answers your question or not.
Thank you for pointing out that congestion issue. Yeah, I think, is there any other questions from the audience? Okay. I guess, yeah, so I guess you should, you can search Dr. Gu's webpage, and if you have further questions, please feel free to send him emails and other contact. So personally, I very much like this study, and finally, I want to again thank Dr. Gu for his nice presentation and interesting and very thorough response to my questions. By the way, I also want to acknowledge this sponsorship from Too Smart Transportation Lab from Dr. Jack Haddad at Tehran Israel Institute of Technology, and their support made the webinar platform possible. And with this, I hope you all have a good weekend, and the meeting adjourns.
Okay, thank you very much, Professor Lee. Thank you all for coming to my presentation.
Thank you, Weihua.
Thank you.
Bye-bye.